Okay. Chapter 11 was our intermolecular forces. Do you guys remember those? Kind of a little. So we had our no, that's fine. Intermolecular forces. Right. And those are the forces between our molecules, right? So we had the types we had were London, dispersion, or just London forces. We had dipole. Oh, the main ones we had dipole. And then we had H bonds. Right. These are the three types. And so for these, so every molecule, for our London dispersion forces, we had every molecule had these. So this was for every molecule. This one was for polar molecules. You had dipole forces when you had polar molecules. And then H bonds were special polar. I don't know, so hopefully that's how you spell special. Special polar. Okay. Okay, so we'll look at some. Let's look at some molecules. I'm pulling these from the chapter 11 worksheet if you want to look. It's just the first question. It's asking specifically about which one has dipole, but we'll just look at all of them, see what has what. Okay. All right, so the 5 we'll look at is BCl3, CF4, CO2. I'll just do it down here. Cl2, and then the NH3. Okay, to do this, we need our Lewis structures. So do that, a quick refresher on how to do that. So we need to know the total number of valence electrons. So boron has 3, chlorine has 7, but there are 3 of them. So 7 times 3 times 7. So what's that, 21, 24? Okay, so boron's probably going to be my central one. Draw my chlorines. Right. And then I put my electrons on my most electronegative one. And here, in this case, it's, I would put more electrons on my chlorines. And right now I have 2, 4, 6. So that minus 6. So I have, what, 18 left? So now I start putting these 18 electrons on my chlorines. So remember, they can at most have 8. So that one has 8. So we'll go to the next one. That one now has 8, and this one has 8. Right, and I'm doing this to see if it's polar or nonpolar. Right, I need to see if it's polar or nonpolar. Make these bigger so you can see them better. Is this ringing bells? Right, okay. Yes, okay. So then I would do all my Vesper stuff for the shape thing. Right, I have 3 electron groups. So this thing is, well, I guess you don't really have to. Well, you're supposed to. You're supposed to do your Vesper saying, oh, this thing is 3 electron groups. So my electron group geometry is trigonal planar. You don't have to write this out. This was last semester stuff, but this helps with polar stuff. This thing is trigonal planar. symmetric and all. We don't care about that. Sure, in a planar. So all these things are like in a plane. They go the right way. And so I would draw my dipoles. Chlorine's more electronegative than boron, so they all go this way. Boop, boop, boop. Right. This thing is symmetric, or all these things, if you do your trigonometry, you'll see that all these vectors will cancel each other out, so this thing is non-polar. Right. You don't really need the vectors. You just look at this and see, oh, it's symmetric everywhere, and it's flat. That also helps. It's flat and symmetric, so it's non-polar. So the only forces this thing has is London. London forces. Okay. Don't leave any room for my chlorine. I'll do this somewhere else. Okay. Move on to our next guy. Same thing, just doing the same thing. Okay, this copper has 4. No, not copper. Carbon has 4. Fluorine has 7, and there are 4 of them. 4. There are 4 of these fluorines. Blah blah blah. What's that? 28 plus 4 is 32. So carbon goes in the middle. Oh. Carbon goes in the middle. So, and then, so that's, I already have 8, so minus 8. And what's that? 24. So I put them all in my fluorine. So that's 6, 12, 18. You see those? Little. 24. Again, it's symmetric everywhere, right? The same thing everywhere. Same elements, or same bond type, I guess you could say. And so this thing, again, is non-polar. Oop, getting my foot. This thing is non-polar. And it, again, just has London forces. Right, continuing the process here, carbon. So we have 4 plus oxygen has 6 times 2. So 12, what is that? Plus 4 is 16. Yes, okay. Okay. C. Okay, here's a. So you'd think it'll look like that, maybe. Or that's our initial guess. So there are 4 minus 4. So I have 12. Right, that would be my initial, might be your initial guess on how this thing looks. But then you see that carbon doesn't have 8. Carbon likes to have 8 around it. Over here, we didn't have. Boron is weird. Boron only likes to have 6, but most of the time, atoms like to have 8 around them. So carbon in this structure doesn't have 8. So we need to move some of these lone pairs and make them bonds. So now that's good. A good Lewis structure, just a little refresher on how to do that. Okay, so this thing is linear and symmetric. You have to be careful with these kind of bonds. This kind of structures. We'll do a different one that looks like this, but isn't like linear, is not non-polar. So this guy right here is non-polar. Switch my colors. This guy here is non-polar. And again, just London's forces. Okay, trucking along, not seeing anything new. Okay, this chlorine up here, so it's just two chlorines bonded together, so they're 2 times 7, which is 14. So I have chlorine, and bonded together. So there's 2, so I have 12 left. So I just put them around my chlorines. 1, 2. Wow, switch my colors, that's fine. Is that 14? 2, 4, 7. Yeah. Okay, so here, since these two are the same atom, there's no dipole there, right? Nothing, no pull to more towards one side. So again, it's nonpolar again, and we have London forces again, right? Right, just refreshing your memory. I'm doing this kind of stuff. All right, I'm gonna erase one of these. Are there any questions so far? Is it all making sense? Or you're remembering it? Whatever. Okay, good. Okay, I'm gonna erase. I'll keep the CO2 because we're about to do example, a different one. Okay. I guess this might also be good for your ACS, maybe. Good refresher on drawing things. Okay, NH3 is the last one on the question. So NH3. Okay, so N has 5 plus hydrogen, which has 1 times 3. So that's 8 total. So hydrogen's never in the middle, so N goes in the middle. Excuse me, H. We have 6, so we need 2 more, so they go right there. Okay. So here now we have some. This thing is not symmetric, right? Because if it was, it would have a hydrogen bonded up there instead. If we want to get technical, this thing is it's tetrahedral, and then I think it's trigonal pyramidal. Right? So it looks like this. So I have H, N, H, and then this is going back. This one's going back. And so I have these lone pairs up here. So I have all my, N is more electronegative, so all my things are pointing up this way, right? Towards the N, and I have nothing pointing down to cancel them. So overall, I get an overall upward pull right here. Overall upward dipole in this case. So this one is polar. This one's polar. So its forces does it have? It has, remember, everything has London, so it has London forces. London. It also has dipole. But also, it has H bonds, right? Maybe you remember. For our H bonds, to have a hydrogen bonding intermolecular force, it had to be, you had to have an H bonded to N, O, or F with a lone pair. Put that in parentheses. Great. That's exactly what we have right here. We have a hydrogen bonded to a nitrogen molecule with a lone pair on it. And so this is hydrogen bonding as well as dipole-dipole. Okay, so that's one of the things we did with intermolecular forces, and then we talked about how it relates to boiling point. So if I had, so the higher my intermolecular force, who remembers how does that affect my boiling point? The higher my intermolecular force is, what does that do to my boiling point? High boiling point, yes. Yeah. Right. Same thing for freezing point, higher freezing point. I think we did viscosity. One of them was flipped. I think it was vapor pressure was opposite. So vapor pressure, double check me on that. I'm fuzzy. I didn't review this stuff. I just remembered it right now. But I think vapor pressure was our opposite trend. All the rest are basically the higher your intermolecular force, the higher your other property, whatever you're looking at. So did that. So we could rank all these boiling points if we wanted to, freezing points, vapor pressures, all that stuff. We did that in chapter 11. Remember, okay, would the highest intermolecular force be the NH3? Yes. Yeah. These are ranked, these are lowest to highest. So yeah, the highest one is the NH3. All the rest are going to be smaller. Now, if they all have, so let's go back. Okay, I want more space. I'm gonna erase all this stuff, or at least our drawings, and I'm gonna erase all this. Keep our forces definitions. Okay, so we had NH3, which we knew was pole. We knew had London, dipole, and H bonds. We had BCl3, had London. We had CO2, which also had London. We had CF4, just had London again. And we had CO2, which had London. Okay. All right, so we'll do it. So here's my list. We got high. This is increasing boiling point. So you can see that NH3 is going to have the highest out of these. Okay, and then we got to rank these guys. Hopefully it's not going to be bad. So I don't know, I don't know if you remember, but your London forces get stronger the more electrons you have. So all right, so this guy has 14 electrons. This one has 4 plus 28 is 32. This one has 12, 16, 21 plus 3 is 24. Right, so since all these have London, well, didn't put an N right there. All these have London. We look at their electrons to see which one has higher. So then the more electrons they have, the stronger their London force is. So my list would go CH4, BCl3, CO2, yeah, CO2 and then Cl2. If I had something that was just polar, so H2O, look at H2O, so it has 6 plus 2, 8 electrons. So we go O, H, H. So remember this one's different. This one's not linear like my CO2 was previously. So remember CO2 look like this. Right, and I said it was linear, right? Because it only has 2 electron groups, so it's linear. This one has 4, right? It has 4 electron groups, only 2 bonds. So this guy is bent. So it's bent. Remember, slightly, maybe a little bit. I might just be ringing bells, but so it actually looks like this, right? And that gets rid of my symmetricness. So this is polar. So this guy's polar. So that's dipole, dipole. Oh, this one also has H bonds. Let's make it SO2. I want something without H bonds, SO2. I want something that's polar. Oh, I know. We'll do CH3Cl. Sorry, I wanted something that was polar that wasn't, that didn't have H bonds in it. Okay. Cl. H. Okay, so this thing has this not symmetric part up here. Oh, you can barely see it, but that's a Cl. This is Cl, and then H's. So this thing has dipole, dipole in London. So when I put it in my ranking now, it just goes right here. It goes under my CH3Cl. Then I've had another one that was tied at this. With this, I would again just look at my electrons to see which one has stronger London forces, and so on and so forth. Make sense? Yep. Okay. So yeah, so that's all we did with this. And then we started talking about phase change stuff. Okay, so no. So we'll move on, I think. Is everyone okay? So we'll keep trucking along in our review. Do I need any of this? No.
Wait, can you explain why CHCl is below NH3 one more time?
CHCl, oh, it's below NH3 because this one only has dipole, dipole in London, but NH3 has dipole, dipole, H bonds, and London. Is that what you're asking me?
Yes, I got it.
Okay. Then we went on to phase change next. We were doing phase change stuff. Phase change. still in chapter 11. So we talked about calculating the amount of heat it takes to boil something with delta H of fusion. So this is fusion is going from solid to liquid. That's fusion. And then delta H of vaporization is the enthalpy needed to go from liquid to salt to gas. So we just did to get our Q, which is our heat again. So this is Q of phase change. You just do N times your delta H for whichever phase change you're going through. So if this is vaporization, Q for vaporization, you do your delta H, and this is the moles of the substance. Moles of substance. And then same thing if that was fusion. Let me make sure fusion is going from solid to liquid. I'm pretty sure it is. Velocities, put solid phase, and dipole. Where's this? Or maybe this wasn't. What is all on the worksheet? Oh yeah, here it is. Here we go. Phase change. Yeah, okay. Yeah, solid to liquid. Okay. And then we did big old, and then you could take that equation and mash it with our Q equals SM delta T, right? And S is our specific heat. M is our mass. This is mass. And that's change in temperature. Again, this is just heat, heat released or absorbed, depending on if you're heating or cooling this thing. Remember, we could take those two equations and figure out, I could ask you questions like, oh, how much heat? Something like how much? Oh, how much? Oh, I want an M, not W. M heat does it take to heat to bring like some amount, some grams of ice to steam, right? So I can ask you questions like that. And if I want to make a diagram, how do I? So I have this is my temperature. So here's my temperature. And I don't know what this axis is. I'm thinking maybe this is phase. I don't know what this axis is. We'll figure it out. Anyway. So we would have different steps. We would start down here. Oh, I guess I should tell you, let's say this is like -5 degrees Celsius. And this is 120 degrees Celsius. Okay. Oh, we can make this. This will be heat. This will be the heat that we added. So this is heat. This is Q. All right, so we would start, I'll do it different. Where's my markers? We start down here. It's our starting point, -5. And then we would go. So we add more heat, and then I'm gonna mark. So this is a melting point of water, right? And this is a boiling point, 100. Right, we all know those. Not too bad. Celsius was made just so that water's things would be those things. So first we would add heat. It would get to 0 degrees Celsius, and then it would stop and until it all melted. And then it would heat up again. Well, I guess it should be a little different slope. It would heat up again until it got to 100 degrees Celsius. That's where these are. It would stop until it turned all to gas, and then we would heat it up all again until eventually we got to our 120. And then to figure this out, to figure out what that Q was, you would just figure it out at each of these steps. So this one would be our Q like 1 equals SM delta T. This is Q of our fusion equals N delta H fusion. Again, Q2, SM delta T again. Okay, so also remember that these S's change with the phase. So S of the liquid, S of the solid. Up here we get Q vape is N delta H vape. And then this guy. So we basically just added up all these Q's that after we calculated them. And this is of the gas. That's kind of small. Right, and then we got our Q total. Q total is equal to Q1 plus Q fusion plus Q2 plus Q vaporization plus Q3, right? And all the problems aren't like that. You just had to, this is like the worst one where it goes all the way through. You might have started in the middle here and then gone up, or in the middle and then gone down. Some other things. There was a problem where we took ice and threw it into water, and then we wanted to calculate the final temperature on one of the worksheets. But this was just another one of the problems that we did in chapter 11, where we just heated up stuff. I could track you. I could just ask you how much heat is it going to take to melt all this ice. That kind of shenanigans. It'd probably be more helpful just to do one of the problems, maybe the worksheet one. I was thinking. That'd be okay. Yes. Okay. So let's go. No, I don't want to show you. This one has the answers on it. Okay. Here's one of the, here's a chapter 11 worksheet problem. I'll share it with you in a second. The answer's not on here. I don't think it is. It isn't. Oh, too close. Oh, there we go. Ignore that empty table. Well, that's weird. Anyway, there it is. Copy it down, do whatever you need. I'll write it on my board. So we got specific heat of ice is 2.03 joules grams degrees Celsius. Water is 4.184 grams degrees Celsius joules, and then delta H of fusion for water is 6.01 kilojoules per mole. Okay, I'll give you a few more seconds to write it down. I'll drink some water. All right. Okay, here we go. So well, I wrote down the gist and here's what's going on. We're just taking some ice, dumping it in some water. And we want to know the final temperature. So I'm going to draw my diagram here again. So let's see, let's do it. Here goes. Right, I'll do it. Hold on, do it this way. This is me diagramming what's going to happen. So I have my ice down here, -5. And so it's going to heat up to 0 degrees Celsius. I'm going to assume that all of it's going to melt, maybe. We don't know. We're going to assume that. Assume all it's going to melt. And then it's going to heat up to some temperature we don't know. And so this is for ice. This is ice. And then my water is just going to cool down. It's at some temperature up here, and it's just going to cool down. So this is my, what's this? This is 26.5. Right, so this is my water. Okay, so this, my ice is just going to heat up, melt, and then heat up again. My water is just going to cool down. Since I'm putting my ice in my water, all this heat that's heating up the ice is being taken from my water to cool it down. So I know that my Q of my ice equals the negative Q of my water. Right? Because it has nowhere, it has to, whatever heat went into this ice came from my water. Or at least I'm assuming that it is. Okay. Okay. All right, so no gripes. Okay. Now I need to figure out what Q of ice is. So let's do that. So the Q of my ice. Okay. So first it's this heating up part. So that's my Q SM delta T. So S ice times the mass of my ice times delta T of my ice again, plus. Now it's this melting part. So the moles of my ice times delta H of fusion. Okay. And then it heating up. So mass of my, okay, here we gotta be careful. So S of water, the mass of my ice, right? Because I'm still leaving, it's water, it's melted now, but it's still that mass, the same mass of that times delta T again. All right, so we can put in numbers. So this is what, 2.03. Oh, I have space. We'll see. 2.03 times my 25.5 times final minus initial. So it'd be 0 minus my -5. So 0 minus -5 is just 5. Plus, okay, the moles of that. So I need this in moles. I'll do that real fast. It's water. So let me, just in case. So 25.5 grams. I know that there's 18.02 grams for every 1 mole of H2O. I did that just by doing the normal molar mass thing. 2 times H is molar mass plus oxygen's molar mass. So what's that? 25.5 over 18.02. So we get 1.42 moles H2O. So right here I get 1.42. Now originally this is 6.1 kilojoules per mole, but right here, this guy's in joules, that's in joules. So I'm gonna change that to joules. So this is gonna be 6010 joules per mole. So 6010 plus the S of my water, so 4.184 times the mass of my ice, so the 25.5 again. And then this times TF minus, right? Because I don't know what the final temperature is, minus my 0, because that's the temperature it's going to start off at. Okay. This is just TF minus 0. So you can see the rest. Okay. So also stop me if you have questions, if I'm moving too fast. So now I'm just doing math. Eight 793.025 plus my 106.692 TF. Okay, so that's my QS right now. This is 8. So we got QF. Now we have Q ice in terms of TF. All right, so I'm gonna write this up here so I don't forget it, and I'm gonna erase that because I don't need it anymore. So Q ice equals 8793.025 plus 106.692 TF. Okay, now we need to do the same thing for the water. So we need to write out what our T water equation is. Keep my picture, so I like it. Okay. Mess it up. Boop. Okay. Where did your Q ice come from? The 8793. So I erased it. So I had it was just this part was these 2 sections. So the Q of the melting, so I did the Q equals SM delta T for this beginning part, this initial part, and then the melting part plus my N delta H. So yeah, and then you plug in your numbers and you get that. At least I think that's what I got. So if you didn't get that, let me know. See, I just plugged in numbers and that's the equation that it spit out. Okay, sweet. Now we do the same thing for our water. So the Q of our water is going to be, now it's easier, it's just this cooling down. So it's just SM delta T, well, be careful, F, S of the water, M of the water, and then delta T. So that's going to be, we don't know what this, oh no, we do know. The density of water is just 1, so 1 gram per milliliter. So it's going to be 4.184 times 125 grams. I think he usually gives you the density of water, but if you don't remember, it's just 1. Times final, which is TF, minus my initial, which is this 26.5. Right, so we'll just multiply these two together and then distribute. So my Q of water is going to be so 4.184 times 125. Okay, so it's going to be 523 TF minus times 2.6.5 my 13,859.5. I'm just keeping all my sig figs, and then in the end, I'm just going to keep 3 because I'm about to do some algebra and I don't want to mess it up. Okay, so now we got that. Now we know what our Q water is in terms of TF. So we can plug in both of the equations we have into this guy right here and then solve for TF. So that's what we'll do right now. I'm gonna erase this. Any questions though? Everyone good? I'm not seeing anything, so I'm assuming yes. All right. So now we have both of our equations, so we'll just set one equal to the negative of the other. So we'll do it this way. So I'm going to do my 8,793.025 plus 106.692 TF equals negative times my 523 TF, excuse me, read this, minus 13859.5. Do some algebra. So what we got 8,793.025 plus 106.692 TF equals 13859.5 minus 523 TF. I get what's that? So I get what's 523? It's this plus my that. Get 6,929.692 TF equals this is my 5066.475, and then TF is that 8.05. Where's my cheat sheet? I went around it somewhere, maybe. Questions? Yeah, cool. All right, this is a really complicated. This is the most complicated one. So that's why I wanted to talk about it. He did ask a question about if there would be any ice left, like would it all melt? So we'll sit here for a second, make sure no one has any. So does anyone have any questions about this one? There's another type that comes from something like this. No, cool. So there's another question you could have asked is, I think he asked it in the PowerPoint, maybe one of his slides, about if all the ice will melt or not. So I'm gonna keep that. Well, I guess I need that. We'll leave it. I want that. I still want that. Me not planning ahead. Okay, 1.42 moles, roughly. Anyway. Okay, so maybe he asked instead, he gives you the same thing, but he asked, will any ice be left? Will any ice be left? So in this case, what you need to check is go and, okay, so I need to see how much energy is going to take all the ice to melt, right? So let's do that. Oh, we actually already did that. So if I want to melt the ice, melt all ice, right? So Q, need to heat it up first, heat it up to 0. So that's going to be my S of ice, M ice, delta T, plus my N of ice times delta H of fusion. I think that's the same. That's going to be the same as last time. So it's going to be 2.03 times 25.5 times 5, because that's 0 minus -5. Great. Plus 1.42 times 6010. And then that's, so Q is going to be my, I think it's the same, it's the 8,000 something. Let me make sure. Yeah, 8,793.025. This is in joules, just joules. So that's how much it's going to take to melt all the ice. And so I need to see how much is going to be to drop the water to 0 now. Drop water to 0, drop H2O to 0 degrees Celsius. It's just going to be Q equals S of my water times mass of my water, times delta T. In this case, it's going to be 0 minus 26.5. So the Q here, I think I already calculated that as well, is going to be, yeah, the 13. So this negative 13, 9, 5. Oh, keep this is 859.5 joules. Again, this was 4.184. Sorry, I skipped a step. Got excited. 4.184, and then this is my 125 grams. And so you get this, and then you compare the magnitudes. So compare magnitudes, or the absolute value. Compare magnitudes. So since this one, the magnitude is bigger than that, all your ice is going to melt. Had it been the other way, had this one had it taken more heat to melt all the ice than to drop the water to 0, then there would have been some ice left. Okay. So yeah, that's another question. Say that again. So you want to look at the absolute values of these. So let's say this is water, this is ice. So when I compare my thing, I want to compare what is Q ice. How does Q, the absolute value of Q ice, relate to absolute value of Q the water? So in this case, our Q of water is greater than the ice, right? The Q to melt all the ice. So that means all of this ice is going to melt and you're not going to have any left. So the answer would be no. Yeah. If it was flipped, right? It was the other way, doing different color, so I don't confuse people. If it was the other way, if I had like the absolute value, my ice was greater than my water, then there would be ice left. Ice left is ice left. Right. Right, we're just comparing these two. Okay. What was I going to say? Okay. All right. That's all I have. Or no, it's 6 o'clock, so we can be done. Unless you guys got questions for me. See y'all later, I guess. We'll probably be doing like exactly this on Tuesday as well. No problem, Luis. Oh, did everyone sign in? Can you give the link again? Yes, I can. No problem. Here, let me grab the link. There you go. There's the link. No problem, everyone. I'll see you all later. Stop the recording.